This is a video summary of the research paper Heralded Optical Entanglement Generation via the graph picture of linear quantum networks, which is set to be published in Quantum Journal. Hi, my name is Seung-Bum Jin, and I am the first and a co-corresponding author of this paper. Our work provides a systematic approach for designing linear optical schemes to generate various heralded multipartite entangled states based on a novel graph method and its translation rules to linear optical components. To explain our current work, I need to summarize the graph method used in the paper, Shortcut to Multipartite Entanglement Generation, a graph approach to boson subtractions, published in MPJ Quantum Information this year. Our goal in this paper was to overcome the difficulty of designing heralded schemes for multipartite entanglement in linear optics. The fundamental elements for heralded entanglement generation are single boson sources, linear transformation operators, and heralded detectors. And then by combining them appropriately, we can generate non-destructive multipartite entangled states. The fundamental problem of this approach is that there has been no reliable strategy to find those schemes systematically. So all the formal works related to this topic have relied on the trial and error methods. And the sculpting protocol is a way of interpreting heralded schemes with simplified forms of operators. So here the physical elements are translated into these different elements, single boson sources and sculpting operators, which are spatially overlapped boson annihilation operators. And this sculpting operator corresponds to combination of linear transformation operators and photon or boson detections at the outputs. And then suitable sculpting operators corresponds to multipartite entangled states. And still, the problem of this protocol was the people couldn't find any reliable strategy to find the schemes for generating various kinds of multipartite entanglement. To overcome this problem, we have introduced a novel graph method, which I named the graph picture of linear quantum networks, or linear quantum graph picture, or simply arXiv picture, as you see here. And in this arXiv picture, all the physical elements and sculpting protocol are mapped to graph elements, which are vertices and colored weighted edges. And then we were able to find some systematic way to generate multipartite entanglement, which are expressed as bipartite graphs. And these bipartite graphs corresponds to sculpting operators for multipartite entanglement. So using all the nice mathematical method properties of the graphs, we could answer to these problems by proposing a systematic graph theoretical strategy. So this was the main result of this paper, MPJ Quantum Information 1067, published in 2024. For review on what the sculpting protocol is and what our graph approach arXiv picture is, see section 2.1 of our current work. An essential question that was not answered in this work is this: how to implement the sculpting schemes in physical systems. Because the sculpting operators are fundamentally mathematical operators, we need a way to install them in realistic physical systems like optics. And we have found a way to do it, and those linear optical elements are dubbed subtractors in our paper. So our work is more than a follow-up paper because it completes the story that we have started in this work. The main question of our work is, as briefly explained in the former page, to find a link from sculpting bigraphs, which is the graph representation of sculpting operators that generate multipartite entanglements, to optical circuits that we can actually build in laboratories. And our strategy is as follows. Sculpting bigraphs can be decomposed into a limited number of elements, which can be translated to optical elements with some translation rules we introduce, with which we can compose a linear optical circuit that generates the corresponding multipartite entanglement. So, if we can impose translation rules from the sculpting bigraph elements to linear optical circuit elements, we can directly draw optical circuits that generate heralded entanglement using the sculpting bigraphs. So in other words, a sculpting bigraph that generates a target state becomes a blueprint for designing the corresponding optical circuit through the translation rules. Before moving on to the main point, we need to explain the dictionary of our graph picture of linear quantum networks, which is summarized in section 2.2 of our paper. The directed bipartite graph representation presented here is the most comprehensive expression of our LQG picture. As you see in this table, all the physical elements of linear quantum networks are mapped to the elements of directed bipartite graphs. In the special modes of LQN are mapped to labeled vertices, and they are labeled because special modes are distinguishable, and creation and annihilation operators are mapped to unlabeled vertices, and they are distinguished by the directions of the edges attached to them. And they are unlabeled because operators are indistinguishable. And special distributions of the operators are presented with directed edges, and their probability amplitude and internal states related to the spatial modes are denoted with edge weights alpha and psi. These are, in general, complex numbers, but for the case of internal state, since we are mostly working on a specific computational basis, these weights are replaced with colors like red and blue. For an example, this graph represents a sculpting scheme to generate Bell state. Since there are 4 unlabeled vertices, which has outgoing edges from them to the labeled vertices, we have 4 creation operators in the input modes, and then at the output modes, we detect or subtract 2 operators or particles which corresponds to the heralded scheme of generating Bell state. And once you check the mapping rule from this bipartite graph to operators, you can directly check that this graph identity holds. And since here red and blue represents the internal state plus and minus, the final state is nothing but Bell state. And this example was a very simple one for our graph representation for expressing the very simple scheme to generate Bell state. And it will be useful when you actually work with more complicated multipartite cases. To do that, in our NPJ quantum information paper, you have defined a very special set of bipartite graphs, which are named effective perfect matching bipartite graphs, or simply EPM bigraphs. An EPM bigraph is a bigraph whose edge is always attached to the circles as one of these three forms. And the reason that we have introduced EPM bigraphs is if a sculpting operator is represented as an effective PM bigraph, then the final state is always fully determined by the perfect matchings of the bigraph. The converse is not true. So it subtracts exactly one single photon from each spatial mode, so automatically satisfies the condition for a sculpting bigraph to correspond to a heralded scheme. See footnote 1 of page 3 in our paper for more detailed explanation on this point. And these are the sculpting bigraph solutions for generating three important multipartite entanglement, GHZ, W, and the superposition of n equals 3 GHZ and W states. You can directly check that they are all EPM bigraphs that satisfies this condition. And this original paper includes all the details on how each sculpting bigraph directly corresponds to a sculpting scheme that generates a specific multipartite entangled state. And this one page summarizes the essential result of our current work. The translation rules from the graph elements of EPM bigraphs to linear optical elements. As I mentioned a few pages ago, the fundamental elements of EPM bigraphs are discrete and limited. And we can consider a set of translation rules that realize those graph elements in linear optics. Here, HWP, PBS, and BS correspond to half-wave plate, the HWP, half-wave plate, PBS, polarized beam splitter, and BS, beam splitter. And whenever a photon bouncing occurs in a path, we replace a beam splitter. We place a beam splitter to split the path of the two photons, as you see here. All the details are explained in section 3 of our paper. A crucial but natural remark is that we chose these translation rules not because they are unique or optimal, but just intuitively natural from the graph representation. Using the translation rules, we can directly design optical schemes for generating multipartite entanglement. As you see, based on this Z-state generating graph, we can directly design linear optical schemes for generating the same target states with our translation rule. This part is directly translated to this part, and this sculpting part to this part, and their path are connected as the edges of the graph. So you see that the topology of this path are exactly, the topology of the path is exactly the same with the topology of this graph. So this demonstrates that the sculpting bigraph solutions become kind of blueprints for designing linear optical schemes. Our scheme requires 2n photons with success probability 1 over 2 to the 2n minus 1. Comparison of our scheme with other schemes for generating GHZ states is given in section 4.1 of our manuscript. An interesting property of our scheme is that it does not have any trusted third party, hence advantages in quantum communications, which is well analyzed in this paper. And we can do exactly the same thing for the W state as you see in this page. Our optical scheme requires 2n plus 1 photons with success probability 1 over 2 to the 2n. And so far as we know, this is the most efficient scheme that generates the heralded W state with single photon sources and linear optical operators. And again, we designed the optical heralded scheme to generate the superposition of n equals 3 GHZ and W state based on this graph solution. And this is the first heralded scheme for the target state to our knowledge. And it requires 9 photons with success probability 5 over 3 squared times 2 to the 7. Finally, some closing remarks are in order. First, I think my explanation so far have demonstrated that this work has provided a systematic approach to design linear optical schemes for generating various heralded multipartite entangled states based on the LQG picture, which was introduced in our formal works, and its translation rules, which is explained in our current manuscript to linear optical components. And our translation rules can be applied to any EPM bigraph schemes, for example, caterpillar graph state generation schemes, which was presented in this paper by myself. And we presented linear optical schemes in polarization encoding, as you have seen so far. However, other types of encoding, including dual rail and time bin, are also possible. And more detailed explanation for dual rail case is given Appendix E of our paper. And also we can consider generalized translation rules for QD cases, because so far we have just discussed about Q bit cases. And this part is still in progress, but we have already announced some partial solutions related to this problem. And actually we have proposed to my knowledge, the most efficient scheme for generating Q-digit z-state with just dn photons, which is the required minimal photon number for generating arbitrary Q-dit n-part GHZ state. And this one is recently accepted by physical review letters. And also, I have introduced a scheme for generating, heralded scheme for generating n-partite n-level antisymmetric and symmetric states in this paper. If you have some questions or comments, do not hesitate to contact me through this email address. Thank you for listening so far.